Hello everyone. Thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Shear Connection, and it is going to provide you a broad overview of the shear connectors and also the analysis of full and partial interaction. I'm going to give you an overview of what I'm covering today's video. First at all, we will have a look at some fundamentals of the shear connectors, then move on to the full and partial interaction theory, then wrap up with conclusions. The design of structures for buildings and bridges is mainly concerned with the provision and the support of load-bearing horizontal surfaces. The construction time can be saved if the floor slabs are cast on permanent steel formwork that acts first as a working platform, and then as bottom reinforcement for the slab. The use of this formwork, known as profiled steel sheeting, began in North America and is now standard practice in Europe and elsewhere. These floors span in one direction only and are known as composite slabs. In composite members, the force applied to this connection is mainly, but not entirely, shear on the longitudinal interface between the materials. As with bolted and welded joints, the connection is a region of severe and complex stress that defies accurate analysis, and so methods of connection have been developed empirically and verified by tests. The property of a shear connector most relevant to design is the relationship between the shear force transmitted, P, and the slip at the interface, S. This low slip curve should ideally be found from tests on composite beams, but in practice, a simpler spaceman is necessary. Most of the data or connectors have been obtained from various types of push-out or push test. The flanges of a short length of steel I-section are connected to two small concrete slabs. The details of the standard push test are shown in this figure. A typical load slip curve shown in this figure. Tests have to be done for a range of concrete strengths, because the strength of the concrete influences the mode of failure, as well as the failure load. Studs may reach their maximum load when the concrete surrounding them fails, but in stronger concrete, they shear off. This is why the design shear resistance of studs with HSC over D larger than or equal to 4 is given in Eurocode 4 as the lesser of these two values of PRD, where Fu is the ultimate tensile strength of the steel, less than or equal to 500 Newton per millimeter square, and FCK and ECM are the cylinder strength and the mean secant elastic modulus of the concrete, respectively. Dimensions HSC and D are shown in this figure. The value recommended for the partial safety, gamma V, is 1.25, based on statistical calibration studies. Next, we will introduce the full connection using a singly supported beam of rectangular cross-section. For each beam, whose strength depended on shear connection between parallel timbers, were used in medieval times, and survive today in the form of glued laminated construction. Such a beam, made from two members of the same cross-section as shown in Figure B, will now be studied. Its span over depth ratio is typical 15 to 25, not shown to scale in Figure A, so that shear deformation is negligible compared with flexural deformation. The loading W per unit length is much greater than the weight of the beam, which is now neglected. Its components are made of an elastic material with Young's modulus E. It is assumed first that there is no shear connection or friction on the interface AB. The upper beam cannot deflect more than the lower one, so each carries load half of W per unit length as if it were an isolated beam of second moment of area BH cube over 12, and the vertical compressive stress across the interface is W over 2B. The mid-span bending moment in each beam is WL squared over 16. By elementary beam theory, the longitudinal stress distribution at midspan is given by the dashed line in Figure C, and the maximum bending stress in each component, sigma, is given by this equation. The maximum longitudinal and vertical shear stress tau occurs near a support. The two parabolic distributions given by simple elastic theory are shown in Figure D, and at the horizontal center line of each beam as shown in this equation. The maximum deflection delta is given by the usual formula as expressed here. The bending moment in each beam at a section distant x from midspan is mx equal to w times L squared minus 4x squared over 16, so that the longitudinal strand epsilon x at the bottom fiber of the upper beam is this equation. There is an equal and opposite strand in the top fiber of the lower beam, so that the difference between the strands in these adjacent fibers, known as the slip strand, is 2 times epsilon x. It is easy to show by experiment with 2 or more flexible wooden legs or rulers that, under load, the end faces of the two-component beam have the shape shown in Figure A. The slip at the interface S is 0 at x equal to 0 from symmetry, and maximum at x equal to plus or minus half of L. The cross-section at x equal to 0 is the only one where a plane cross-section through both members remains plane. The slip strand is not the same as slip, in the same way that strand is rate of change of displacement. Slip strand is the rate of change of slip along the beam. Thus we have this equation. Integrate this equation. We obtain this expression. The constant of integration is 0, since s equal to 0 when x equal to 0, so that this equation gives the distribution of slip along the beam. Now we assume that the two halves of the beam shown in this figure are joined together by an infinitely stiff shear connection. The two members then behave as one. Slip and slip strand are everywhere 0, and it can be assumed that plane sections remain plane. This situation is known as full interaction. For the composite beam of width b and depth 2h, I equal to 2b times h cubed over 3, and the elementary theory gives the midspan bending moment as w times L squared over 8. The extreme fiber bending stress is this equation. The vertical shear at section x is Vx equal to w times x, so the shear stress at the neutral axis is this tau x equation, and the maximum shear stress is this tau equation. The stresses are compared in Figure C and D with those for the no-composite beam. The provision of the shear connection doesn't change the maximum shear stress, but the maximum bending stress is halved. The midspan deflection is this equation, which is a quarter of the previous deflection. Thus, the provision of shear connection increases both the bending strength and the stiffness of a beam of a given size, and in practice leads to a reduction in the size of the beam required for a given loading, and usually to a reduction in its cost. In this example, but not always, the interface AOB coincides with the neutral axis of the composite member, so that the maximum longitudinal shear stress at the interface is equal to the maximum vertical shear stress, which occurs at x equal to plus or minus half of L and is 3WL over 8BH. The shear connection must be designed for the longitudinal shear per unit length, VL, which is known as the shear floor. In this example, it is given by this equation. The total shear floor in a half span is found by integration of this equation to be 3WL squared over 32H. A useful rule of thumb is that the resistance on the shear connection for a beam should be an order of magnitude greater than the load to be carried. It shows that shear connection must be very strong. In design based on elastic behavior, the shear connectors are spaced in accordance with the shear flow. Thus, if the design shear resistance of a connector is PRD, the pitch or spacing at which single connectors should be provided, P, is given by P times VLx less than or equal to PRD, so that we have this equation. This is known as triangular spacing, from the shape of the graph of VL against the X as shown in this figure. In studying the simple composite beam with full interaction, it was assumed that slip was everywhere 0. However, the results of push tests show that even at the smallest loads, slip is not 0. Therefore, it is necessary to know how the behavior of a beam is modified by the presence of slip. This is best illustrated by an analysis based on elastic theory. It leads to a differential equation that has to be solved afresh for each time of loading, and is therefore too complex for use in design offices. Even so, partial interaction theory is useful, for it provides a starting point for the development of simpler methods for predicting the behavior of beams at working load, and finds application in the calculation of interface shear forces due to shrinkage and differential thermal expansion. One end of the beam to be analyzed is shown in Figure A. Figure B shows in elevation part of it, of length dx, and the distance x from the midspan cross-section. Transverse profiled sheeting is assumed to be present, and the two components are shown separated. The slip at top flange level of the steel beam is S at cross-section x, and increases over the length of the element to S plus ds over dx times dx, which is written as S power plus. This notation is used in this figure for increments in the other functions of x, which are mc, ma, nc, na, vc, and va. These are respectively the sagging bending moments, tensile axial forces, and anti-clockwise vertical shears acting on the two components of the beam. The suffixes C and A indicating concrete and steel. They are shown in the directions taken as positive. From longitudinal equilibrium, NC equal to minus NA, the interface vertical force R per unit length is unknown. Let the interface longitudinal shear be VL per unit length, so the force on each component is VL times dx. It must be in the direction shown, to be consistent with the sign assumed for the slip S. The stiffness of the shear connection, shear force per unit length per unit slip, is Kc, so the load-slip relationship is VL equal to Kc times S. The method is to deduce equations from equilibrium, elasticity, and compatibility, and by elimination obtain a differential equation relating S to X. Then solve it and insert boundary conditions. These include zero slip and midspan from symmetry, so S equal to 0 when X equal to 0. At the supports, M and N are 0 in both materials, so the difference between the longitudinal strength at the interface is the free shrinkage strength in the concrete, epsilon Cs. As the tension positive convention is used, shrinkage strength is a negative number. With this sign convention, we have this equation. Now we see the equilibrium condition. Resolve longitudinally for one component. We have this equation. For moment equilibrium, we obtain these two equations. The vertical shear at cross-section x is W times x, so that we obtain Vc plus Va equal to W times x. From this figure, we have this DC expression. Thus, after the mathematical derivation, we obtain this equilibrium equation. For elasticity, in beams with adequate shear connection, the effects of uplift are negligible in the elastic range. The two components must then have the same curvature. Kappa and simple beam theory gives the moment curvature relations. Using a modular ratio n, that allows for creep, and the kappa equation shows here. The longitudinal strengths in concrete and in steel at the top surface of the steel flange are expressed the epsilon c and epsilon a equation, where epsilon cs is the free shrinkage strength of the concrete, a negative number. Now we see the compatibility condition. The difference between epsilon c and epsilon a is the slip strength. So from DC epsilon c epsilon a equations, we obtain this expression. The differential equation for S is found by eliminating MC and MA from VL, equilibrium and kappa equations. Then we obtain this equation. Differentiating ds over dx equation and eliminating kappa, Na, and Nc and VL leads to this expression. To represent the result in a standard form, these symbols are defined as alpha square and beta equation, which gives this expression. Inserting the boundary conditions, it gives the expression for longitudinal slip as this equation. Expressions for the slip, slip strength, curvature, and stresses throughout the beam can be obtained as functions of x. All results are proportional to the loading W. In full interaction analysis, the slip is 0, and the results depend only on the bending moment and shear force at the cross-section considered. Here, they depend on the loading, boundary conditions, and shear connection for the whole beam. From conclusions, what we learned: composite slabs comprise reinforced concrete cast on top of profiled steel decking, which acts as formwork during construction and external reinforcement at the final stage. A shear connection is a joint that allows the transfer of shear forces between two members. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.